things that look like hyperbolic dynamics, but in this case, all topological objects. And the idea that I'm going to discuss here is trying to understand a little bit of Aubry-Maher sets for trying to understand how is dynamics, conservative dynamics for surface homeomorphisms. So let me start with some picture of what is a typical error-preserving dynamics on surfaces. And there is for here one simple family which is well studied, which is the Chirikov-Taylor standard map. A lot of you have seen this, and what you see with this example of error-preserving dynamics is that usually what you see here is that you see, well, you look here and you say, oh, there are some periodic islands, some regions that are going to be some things which are homomorphic to open topological disks, which are periodic. After a few repetitions, they are invariant by some power of the function. And then here, I have another periodic island of higher period. And in between these things, sometimes you see things which are some curves, invariant curves, which, for instance, here is a curve where every point here is sort of turning with some speed around the annulus or around the torus. They are all moving in a single direction. And you have another curve here, for instance, which is turning perhaps with a different velocity, and this region in between them is like, well, if I draw it again here, it would be something like an annular region, at least topologically speaking, where these points are moving upwards, these points are moving to the right, these points are moving to the left, and in between you have some points which go from below to the top, from the bottom boundary to the top boundary. And you also have some points which go from the top boundary to the lower boundary. So this kind of region has sort of a diffusive behavior, and you have inside this region a lot of things like, oh, you see the islands when points rotate with some rational speed, but you might have some things which have different speed. In between, sometimes you have a region which have bounded by two of these curves. Sometimes you have several curves in between. And even if you look inside one of the islands, so if I took a closer look of the island here, this island, for instance, here, then if you look inside the island, you see sort of the same result. You see other curves here and other islands, and in between some maximal intervals where you have some topological annulus, and the dynamics in this annulus is really interesting. And perhaps sometimes you also see things depending on, well, if in this case, if you're in the torus, sometimes you also have this very large diffusive region, which now this is not homotopic to an, it's not homomorphic to an annulus, but it's a more complicated region. So this is what you actually see in simulations, and is this what we actually see in general? So, and what can we say, or how can we describe this region? So let me just see if I go now over everything here. Okay, so the existence of the periodic topological disks, this invariant curve or continua. I mean, again, I'm usually going to talk about things on the C0 point of view. So these curves are usually not curves. They are just some strange connected compact sets which have some interesting topology, and they may be much more complicated. They might be things like, for instance, a pseudo-circle, which is a really nasty object and something like that. But the idea, or at least the cartoon picture, is the same. You have something like curves invariant, and you have the regions between the curves, and sometimes these special regions in between. And the question is, well, how much can you say? So how much dynamics is there in between these two curves on in one of these diffusive regions, which are usually annular regions in particular? And the idea here, so there is to try to understand, so what's the dynamics in these annular regions? And I'm going to use one approach, which is to try to see it through the rotation theory. So it's try to detect objects and to describe objects, at least looking at how they turn around. So you have an annulus, and then you have this annulus, and you have some invariant objects here, and you want to say, okay, does these orbits, like, are they turning around in the annulus with some prescribed speed, and can I detect different dynamics just by looking at the speed that things are turning around in the annulus? Okay, so just, well, this is a very basic reminder, but just to recall everybody what's happening here. So if I have an homeo of the circle that preserves orientation, and I take a lift of this homeo to the plane, then for every point in the circle, there we will have a well-defined rotation speed, which is the rotation number. And this rotation number is the same, the Poincaré rotation number. Everyone turns with the same, everyone has a speed, and the speed is equal for everybody, and everybody's turning around in the circle at the same speed. If this number is rational, then you have a periodic point, and if again, if you have a periodic point, it's rational. So it's if and only if either the Poincaré rotation number is rational and you have periodic points. If it's not, if it's rational, then you're going to find a unique minimal set. And this minimal set dynamics there is semi-conjugated to the irrational rotation. It might be the whole circle, or it might be some Cantor set, and you're rotating around with this Cantor set. So this works well in one-dimensional, but now we're going to study, and I'm going to focus the work here. I should have said this, most of this work is with Jonathan Conejeros, but again, it uses a lot of techniques that were developed in my recent work with Conejeros, and also a lot of the techniques and partial results that I used are from my work with Patricia Calves. Okay. Okay, so here I'm going to just to state the settings. I'm going to have my annulus A. It is my annulus A, and this is the closed annulus, and the universal covariance is going to be A tilde, and I'm going to have some projection P1. So projection P that goes from my universal covering to my annulus, just a fixed notation, and P1 is just the projection on the first coordinate. And usually I'm going to have a homeomorphism of A, which preserves, which is isotopic to the identity. In this case, just means that it preserves the boundary components. You fix the boundaries and you preserve orientation, and this will be usually lived. It can be lived in more than one way, but they just differ by a single integer, a single displacement on the result. So you can have the lift of your homeo on annulus, and then you're going to have something which is the displacement function. So this is defined on the annulus, but if I take a point Z on the annulus, and then I go to the universal covering, I take any point Z tilde which projects by P on this. I look where this point Z tilde is going to end, and I calculate what is the horizontal displacement. This distance is the theta of Z. It just depends on Z, it doesn't depend on Z tilde. So it just measures how much you moved on the universal covering to the right or to the left. Okay, and it will be good to have a couple of good, simple examples to keep in mind. This one is easy. It's just, well, this is the drawing, it's the time one of this flow, which means that, oh, I have points here which are moving one step to the right at each point. I have points here which are moving one step to the left at each iteration, and all the other points start at the top boundary and then at the lower boundary. This is not conservative dynamics. This is not error preserving. And you see, okay, I have points which move asymptotically with speed 1. I have points which move asymptotically with speed -1 or with speed -1. I mean, all the points in the lower boundary are fixed and move -1 to the left every time. So they have speed -1. These points have speed 1. And all the other points in between have, if you look at the future, they have speed 1. If you look at the past, they have asymptotic speed -1. So you only see two possible velocities, 1 and -1.
So what is this big F?
It's the lift of the, so little f is the map from the annulus, big F is the, okay, not the annulus, here it should be. This is the map from the annulus, and big F is the map that goes from the strip to the strip.
Is this formula correct?
Huh?
Is this formula correct? I understand the picture, but
I think so. No, I mean, if
fine, whatever. Yeah, the picture is
I
correct.
think the formula is correct, but yeah, I mean, and if it's 0, this is fixed. If it's 1, it's the vertical coordinate is fixed. If it's 1, you're moving 1 to the right. If it's 0, you're moving 1 to the left. Yes, I think it's right. Okay. But I mean, the formula is not important. Just understanding the dynamics, the picture is sometimes more relevant than the formula. And the second example, it's well, this is more simple. I'm just moving. This is just a sort of a dentist. I'm moving. Top boundaries are moving more to the right. Lower boundaries moving to the left, and every height is fixed, and everybody's moving with a different speed. So here, every point here has a well-precise speed, and the speed you have depends on your height. Sometimes you have a higher speed. The higher you are, the higher speed you have. In both these examples, all points have a well-defined speed, but the thing is, you don't even need to have a well-defined speed.
So the first example is a diffio. No.
Yeah, I think so. No,
no, the derivative is 0. The Jacobian is 0. No? Okay. The two wild.
Okay, it's not a diffio, but it's homeo. I mean, I said, did I say diffio? I'm sorry. Okay.
So it has to be volume preserving.
No, I'm here. I'm just doing rotation theory. It's not volume preserving here. The second one is volume preserving. The first one is not. It's obviously not. Okay, I just want to use this to show different concepts. This is conservative. This is not. And when I'm going to do here, it's okay. So I'm going to try to do rotation theory and try to see, okay, how many different ways can I see rotation from which different objects? So I start by having a set of, I take my dynamics and I've set the set of F invariant probability measures, okay. And then I have MER, which is the set of ergodic probability measures, which are invariant by my dynamics. And I can define the rotation number of a measure by, okay, the rotation number of a measure is just the integral of this displacement function. It means, well, what's the average displacement that you have? Sometimes some points move more to the right, more to the left. And you define something which is the measure rotation set, which is the union of all rotation number for measures. This is always an interval because, well, this set is convex, and this transformation is a linear convex in R, so that this is compact and convex. This is always a closed interval. So you only have the rotation set through the measure. Just looking by the measures is a closed interval, and we can define the ergodic rotation set by just the subset of the ergodic measures. Okay, I just look at what possible ergodic measures I have, and I look what are the possible rotations for ergodic measures. This is the point of view of just looking by spatial average, but I can also try to think of time average. So given a point in the annulus, I can try to define what is the rotation number of this point. And I say that a point has a rotation number if, in particular, this limit, which is how much you have moved, the average speed you move to the right, exists. And I'll denote this by the growth z of f. That means, this is the rotation number of the point z for the specific lift I took of my dynamics. Problem is, and we're going to see this is not very difficult, this number doesn't need to exist. You might have points that don't have rotation number. But if your point has a rotation number, you say, oh, this is the rotation number of the point, and you define the punctual rotation set as just being that, okay, the punctual rotation set is the collection of all possible rotation numbers for points. You might, a point is a vector, a number is in the punctual rotation set if you have some point that rotates with that particular speed, if that limit exists. Okay, and there is a final notion that I want to bring, which is the idea that when you have a compact set that has a single rotation, and say that a compact set has a rotation number, if it holds that the compact set is first invariant, it's an invariant compact set, and second, if every point in this compact set has the same rotation number. So in particular, you're going to find some minimal set. So a closed set such as dynamics there is minimal, where every point in this compact set has the same rotation number. Just the most simple example is just take a periodic orbit. Have a periodic orbit, then the orbit itself is going to be a compact set with a single rotation number. It should be noted that you can have minimal sets that don't have rotation number. You can even have one set, which is a compact invariant minimal set, but points inside this minimal set have different rotation numbers. It's not difficult to construct things like that.
Fabio, sorry, you have there is some condition that guarantee that giving a rotation number, the points having that rotation number is a compact set. This is
no. I'm going to discuss when you find a compact set. That's the main result on the talk is to say when can I be sure that I have a compact set that has a rotation number.
Okay.
But the set of points that have a given rotation number, it's not usually a compact set, I guess.
Is to detect when it's a compact set, but okay, go ahead. Thank you, Fabio.
So, and then I'm going to define this, which is the Aubry-Maher rotation set. In some sense, is the stronger form of realization of rotation. Is that you say that a number is in the Aubry-Maher rotation set if you find a compact set that has that precise rotation number, that every point in that compact set rotates with the same speed. Okay, and it's not difficult to see that this sort of inclusions hold. I mean, if you have a compact set that has a rotation number, then you have a minimal set there, and you can find an ergodic measure which is supported in this minimal set, and then the rotation number for that ergodic measure is going to be the same rotation number of the compact set. So these guys are obviously containing this. If you have a compact set, you have an ergodic measure that's going to realize the same vector. And if you have an ergodic measure, then almost every point in the support of the ergodic measure is going to have the same rotation number. And if you have a point which have a given rotation number, then you can just do a Krylov-Guliov kind of limit thing and find a measure which has the rotation, that same rotation number. So this guy is containing this guy, which is contained. See, I don't know. I think I clicked something here which I shouldn't. No? Okay. 1 second. Okay. So this one is containing this one, which is containing this one, which is containing this one. And again, if you look at this guy is an interval, but the thing that
okay, can you recall what AN, erg?
Okay.
Okay, good.
Why is this? Okay. Okay. This is from Aubry-Maher, which is when you have a compact set that realizes the rotation number. These are just by the ergodic measures. These are the points, and this is by any measure. So I'm saying that if you have a compact set with a rotation number, then you're going to find an ergodic measure with the same rotation number, because you have an ergodic measure which supported in this invariant compact set. And if you have an ergodic measure, then typically every point in the support of this measure is going to have the same rotation number. And if you have a point with a rotation number, you can do a Krylov-Guliov kind of limit. Just take the delta function on the average of the delta functions on pieces of orbits, and you're going to find an invariant measure with that rotation, with same rotation number. So these are not very difficult inclusions. It's just saying that this guy is smaller than this guy, it's smaller than this guy, it's smaller than this guy. And if you look at the example 1, then the rotation set, the example 1 is the one which was dissipative. The rotation set for measures was the whole interval, but in the other case, the rotation set for points is the same as for ergodic measures, which is the same from Aubry-Maher sets, which is you can only see two different velocities, either 1 or -1. And meaning because the ergodic measures here are just the fixed points at the top boundary or in the lower boundary. That's the only ergodic measures we have in the system. And well, it's not very difficult to convince yourself, but don't want to spend too much time here on that. But you see, you only see either -1, 1, or just the two ends. And in example 2, it's easy to see that if you take any horizontal circle, that's an invariant compact set, which has a different rotation speed. So here, all 4 different concepts are the same, meaning that the weakest realization of a rotation is also the strongest realization of a rotation. If you have a velocity here, you're going to find that you actually have a compact invariant set all rotating with the same speed. Okay, and
the first example was the read flow, the type of read flow.
Yeah, the read flow. The first example was the read flow. This one was just the bent twist. The second one was the bent twist. Okay. So the first example was dissipative. The second example was error preserving. And the idea is to say, okay, this is if you are in the error preserving case, this is what's going to happen. So I told you about different.
The dissipative proper was essential to have this dichotomy, or just an artifact of your example?
No. I mean, the main result of the lecture, I don't want to go there, but before, but what I'm going to prove is that if you are error preserving in the annulus, then the 4 concepts are the same.
Okay, sorry.
Okay. So the main theorem afterwards is just saying, okay, if you are error preserving, then there is no difference between any of that. If you have any weak form of realization, is equal to the strongest form of realization. Okay. So before I go there, let me just show what some of the initial realization results on these ideas that you find some things on some part of the dynamics, and you deduce that you have more objects which you did not know that were already there. So the first one is the PoincareB theorem, which says that, okay, if I have here in the annulus, I have some error preserving dynamics on the annulus, and say, okay, if the top boundary rotates one way and the lower boundary rotates the other way, then I'm going to find in here 2 points which are fixed. So this is telling you that whenever you have some twist condition, this kind of twist conditions, that meaning that you have things rotating one side and the other side, then you're going to find intermediate things in between. This is for error preserving, an error preserving map. And basically what you're saying is that if you look at the rotation number of the top boundary and the rotation number of the lower boundary, in between every rational, you just take a power of dynamics if you want, every rational point is going to be realized by a periodic orbit. So you can just, looking at what happens on the top boundary and lower boundary, you find a lot of periodic points. You find infinitely many periodic orbits and different things just as a direct consequence of this theorem. The second one is for twist homeomorphs. I mean, I'll say that a twist homeomorphism is just a homeo of the annulus that has the property that any vertical segment is sent to a curve which projects injectively in the first coordinate, meaning that locally projects injectively. So just meaning that you take any vertical segment and it's sent to something which is slanted. It has some slanted property. I mean, I'm not using differentials here because I want to treat this all as just from topological point of view. But the idea is that you have some sort of shear, meaning every point which is in the same vertical, but in the same vertical line, if you're higher, you're going to rotate more to the left, to the right. And in particular, points at the top boundary is going to rotate more than points on the lower boundary. So just by PoincareB theorem, you have a lot of periodic points which are there. But in this case, if you look at twist diffuse, but of the closed annulus, you have something like Aubry-Maher theory, just using rational techniques mostly. And you're going to show that in this case, it already was known and hold that weak realization was the same as strong realization, meaning that for everything from top to bottom is going to be realized. And for any rational point, you find a periodic orbit with minimal period. And if it's not rational, then you either find an invariant circle, which has some irrational rotation number, or you find some invariant Cantor set. And the dynamics in this Cantor set is semi-conjugated to the rigid rotation. And in between two invariant circles is we had what is called the matter region of instability. I'll define this better. It just means that, okay, I find some invariant circle, I find some other invariant circle, and I assume that I have no invariant circles in between these two, and they rotate at different speed. Then this means that there is some orbit which is born in the lower circle and dies in the upper circle, and you also find some orbit which is born in the upper circle and dies in the lower circle, meaning the alpha limit is contained in the lower circle and the omega limit is contained in the upper circle, and vice versa. So it's some sort of impossibility. I mean, you cannot cut this region in between by any invariant set. And this was an important result, and all of this assume that some very strong properties. Being a twist map is not exactly an easy, simple requirement. But then when you go to the general annulus ordinals, there is this important result by Handel that came afterwards that proved that even if here you don't need to assume that you have an error preserving dynamics. It just says that, okay, if you look at the punctual rotation set, this is always going to be closed. And if you look at what happens, which points are in the punctual rotation set but are not in the ergodic, in the punctual rotation set but not in the ergodic, remember this one is at least smaller than this one, then you might have some points. I mean, it's not like you don't have examples of this not holding, that this set and this set is the same. No one knows if these sets and these sets are the same. But you might have, if it happens not to be the same, then this has to be a discrete set. So a big open question is the ergodic rotation set the same as the punctual rotation set? Does it mean that you always have an ergodic measure? For any point where you see, do you also see an ergodic measure of this property? And an intermediate, or important result, which is intermediate and was used, it's important to use, it's the theorem by Franks that say that, okay, in the error preserving case, if you look, the rotation set, okay. If you look at how this thing is an interval, is always an interval, AB, but the theorem by Frank say that if you preserve area, then what you're going to see is that for any P over Q which lies in AB, there exists a periodic point. Associated. So this means that any rational in between AB is going to be realized by a periodic point. And this is in particular, since by the theorem of Handel, this rotation set of points is closed, this means that every point is going to be realized. Every number in the rotation set is going to be realized by point. You're going to find points rotating with any speed you want. But you don't know anything from below, or you don't know anything, at least from ergodic. Is it true for ergodic measures, or is it true for Aubry-Maher sets? And then the final result, this is from Patrice, like always from some while ago, is that, okay, if you assume diffuse, then you're going to have the strong result here, which says that any weak realization is equal to the strong realization. You're going to find both area preserving, if you're going to find any weak thing, you're going to find a compact invariant set that has the same dynamics. And so now the main theorem that I'd like to discuss here a little bit is that this joint work with Jonathan Bonequeiros, which says that, okay, this diffuse thing is unnecessary. And if you are error preserving, then if you find any measure which has a rotation speed, then you're going to find at least one compact invariant set that has this same rotation speed. You always find for any number in the rotation interval. So that this thing is that the compact invariant sets. And this thing is any measure.
So capital F is the lift? Capital F is the lift, or?
I did not hear, Catherine, sorry.
You write that tilde F is a lift to the universal covering space. That's the statement of the theorem?
Oh, okay, sorry. This is, yeah, okay.
Okay.
Okay. No,
this is capital F, yes. I mixed notations in the statement of the main, sorry. And it's just saying that if I take any error preserving, then you actually see everything here. See the compact invariant sets, whatever you give any two things rotating at different speeds, I'm going to find for any rational in between some compact invariant set that realizes this. Okay, and so let me just, this is just one of the important components here. I'm saying that my closed annulus is a region of instability. I think I already said this, but just to be sure, it's called the matter region of instability. If I can find one point here such that the orbit in the future goes to the top boundary, and in the past it came from the lower boundary, so the alpha limit and the omega limit are in different boundaries. So this guy is one orbit that goes this way, and you also find one orbit, let me choose a different color, that goes the other way, from the top boundary to the lower boundary. I don't want to be very technical, but there is an intermediate idea of instability, which is called the Birkhoff region of instability, which says that you cannot find any two subannuli which are invariant. But for those which are more directly connected to the area, whenever I'm going to speak of region of instability, I'm just going to speak about matter regions of instability. Okay.
Are they related, region matter and Birkhoff?
Birkhoff is weaker than matter, and usually one does not imply the other one. I mean, for instance, you can have weak mixing irrational rotations which are rigid. So these things are, if you look in the annulus, they are the annulus is an Birkhoff region of instability because you can go from arbitrary low to arbitrary high and back, but you have no orbits which have omega limits which are in either boundaries. So Birkhoff is weaker than matter in this sense. And one object that is going to appear sometimes, let me just not lose. Okay, just a second. Okay. One object is going to appear a lot is something called the rotational horseshoe or rotary horseshoe, depending on the names, which is usually your typical horseshoe, but this is a horseshoe that in some sense in the annulus it turns around in the annulus and gives one full turn in the annulus at least. So the idea here is that I have some set Q in the annulus. Okay, in the annulus it's going to look like this. I have here my annulus, and I have here some square. Okay, and the image of this square is going to be something which goes like this. The image turns at least once around in the annulus, and it forms a horseshoe. I think that the picture on the left is better than the picture on the right, but it's just a horseshoe that wraps around the whole annulus. And if you have something like that, then you can do some symbolic dynamics, just saying, oh, where did I stay? Did the image stay in the same component in the lift, or did I move to the right? And you can do some symbolic dynamics, and you can do some rotation theory just using the symbolic dynamics. And it's not difficult from seeing that when you have these, you can have like minimal sets which don't have a prescribed rotation number, because you can have a minimal sequence. Which is, the closure of the orbit is minimal and doesn't have a well-defined frequency of zeros and one. Rotation is translated into frequencies of zeros and ones. You want to know how much I turn on the lift, I just sum the set of indices, and I say, okay, how many times did I move to the right? How many times I stayed in the same way? And you can just play a lot, and you have a lot of tools from symbolic dynamics to say, oh, when I have a rotational horseshoe, then I can find things which have given any irrational number, I can find a minimal set which has this irrational rotation number, just by playing with symbolic dynamics. That's not really a difficult thing to do. So this is, I mean, just take...
Sorry, Fabio, this semi-conjugacy is very bad, or you can say, for instance, something about how they are the pre-image of the... This, I mean, in my case, this thing is going to be, this is just homeo, so that the things that appear here can be really nasty objects, okay, in principle. So that I'm drawing this, and the important thing is that, okay, this guy and this guy cross, and if I take any line here, it's going to have, the image is going to have two disconnected components crossing from one side to the other. So, but again, I cannot say much from what's happening here. I mean, this set might be really bad. Whatever is the pre-image of any sequence can be really bad. Okay. Okay. But whenever I find something like this, then I'm going to say, okay, I'm going to have a good horseshoe that's happening. And I mean, the typical case, or for the C1 case, is when you have some point P, just saddles, and some point P, and you have some point Q. And okay, I just have these two hyperbolic saddles, but the thing is that P and Q, they rotate with different speeds on the annulus. And then you can find a horseshoe which looks exactly like the one I did here. I mean, P is a saddle point, Q is a saddle point, but they might be fixed points in the annulus, but when you lift them, one is a fixed point and the other one is a point which is moving one to the right. And then you can find horseshoes like this. This is the sort of object that you're going to find in smooth dynamics. Okay. And one of the main results here that I'm going to use, it's one of the main things which is hidden. I left space for trying to say a little bit of this in the end, but I'm doubtful I can get over there. So it's in the end to save space. It just say that, okay, if this annulus is a region of instability, and I have here 2 points, one point P1 and a point P2, and they are moving with different speeds, then I can find this same sort of heteroclinic cycle connecting P1 and P2. Not P1 and P2, but a periodic point which rotates with the same speed of P1 and a periodic point which rotates with the same speed of P2. So that whenever I find two periodic points with different rotation speeds, if I am in a region of instability, then this follows from my work with Patrice on something we call forcing theory. It's kind of a Brouwer theory. And then you can actually find some special horseshoe here. And in this way, you say, okay, any rotation number in between the rotation number of P1 and the rotation number of P2
is going to be seen by a compact invariant set. But this only holds when you are in a region of instability. And then the first result, one of the important results with Jonathan, is that, okay, if I am in a region of instability, a matter region of instability, then in fact, if I just look at regions of instability, what you're going to find is that the rotation set for compact sets, for the Aubry-Maher rotation set is the same as the strong one. Let me try to understand, just to say a little bit of why I'm trying to do this. Well, if you have an error-preserving homeo of the annulus, then you're going to see that, well, what you're going to find is, oh, sometimes I find some strange continua here, which breaks the dynamics. And sometimes this accumulates in something, but in between them, these blue regions are going to be regions of instability. So the first part of the theorem is saying that, okay, for region of instability, if I lie inside one of these regions, just a region of instability, I can realize everything. And then you will have to understand what happens. Oh, what happens when you have several regions of instability, one stacked next to the other. Okay, so the first part, which says, okay, if I am in a region of instability, I can realize everything. Let me just give a very brief idea of the proof. So what's the main ingredients to show this part? And it's like this. I am a region of instability, which means that, okay, this is a region of instability. I have different rotation points in the boundaries, or in whatever different rotation points I have inside my annulus. That means that by theorem by Franks, every rational point is realized inside the annulus. For any rational number is realized by a periodic orbit. So I have the rotation set is an interval. Frank's theorem tells me that, okay, any two rational points inside this interval is realized by a periodic orbit. And then the result of Patrice says, okay, if I have any two rational numbers here, I'm going to find a horseshoe that sort of connects these 2 points. Think of this as a clinic cycle between these two periodic points with different rotation number. So between any two rationals, I can find a horseshoe. I can find any rational in between these two. So the difficulty here goes that, okay, any rational which is in the interior, I can find two rational points, one which is lower than this irrational, one which is higher than this irrational, and I find a horseshoe that contains this irrational in between. So the only question remaining is, can I realize the extremal points? The extremal point, I mean, the rotation set here is going to be some interval AB, and the only question is, are A and B realized by compact sets? And the answer is, okay, at first I don't know if A or B are realized by compact set, but I know that since the extremal points of the set of invariant measures are ergodic measures, then at least A and B are going to be realized by some ergodic measure. Meaning that this is the image of the rotation set, measure rotation set is the image by a linear function of the set of invariant measures. The set of invariant measures is convex, and the extremal points are the ergodic measures. This says that, okay, the extremal points of the rotation set need to be images of rotation vectors by invariant measures. And in this case, I say, okay, A and B are realized by an ergodic measure, meaning that I'm always going to have an ergodic measure whose rotation number is A, and I'm going to have an ergodic measure whose rotation number is B. And now there are two possibilities. The first possibility is that either A or B are the rotation number of the boundaries. If you are the rotation number of a boundary, you already realize, because the boundary realizes this rotation number. If it's not, then using a technique we've developed with Patrice, this is the hard point, but just to give an idea, is say that, okay, if these two boundaries rotate with different speed, but larger, but I have some point, some ergodic measure, which rotates with some speed which is smaller than these two boundaries, and it's extremal, meaning the set of rotation numbers is going to be A, B. My ergodic measure rotates with rotation number A. And there is a lemma here that says that, okay, all points here cannot move too much to the right or too much to the left more than A. You sort of rotate with the same bounded deviation by the number A. You cannot deviate for what is the maximum, what the speed of the ergodic measure is. You cannot deviate because if you have a deviation to the right, you must have the same deviation to the left. And this would create the velocity which is smaller than A. And since the measure is ergodic, you cannot deviate to the right, just to the right, because then in the average, you're going to have more than rotation A. I don't want to go into too much technicality here, but it just says that if in this case, then you can show that if the extremal point, which is the difficult case, was realized by ergodic measure, then the whole support of the ergodic measure needs to move with the same speed because it cannot move more to the right or more to the left. So you're saying that in the end, the support of the ergodic measure is going to be your Aubry-Maher set. This is not what usually happens. You have a lot of ergodic measures, which you might, for instance, have that you preserve Lebesgue. Lebesgue is ergodic, and the rotation set of Lebesgue is somewhere here, some row of Lebesgue here, meaning that it's not true that all points of the support of ergodic measure are going to rotate at the same speed. But for this case, if you're an extremal object, then you can use that by being extremal, you cannot deviate neither to the right nor to the left, and everybody needs to rotate at the same speed. Okay. So, okay. So the second part of the ingredient of the theorem is in understanding what's an essential continua. I'm going to be a little loose here. I mean, I have this annulus, and I'm going to have an essential continua in the interior of the annulus if I have some compact set that K such that the complement of A has two different connected components, one which includes the top boundary and the other one which includes the lower boundary. It's just some object that cuts the annulus in two pieces, one which is above itself and one which is below itself. And simple way is just an essential circle. You can find essential circles. This is sometimes invariant by dynamics. And the thing is, what kind of these objects appear naturally as the boundary of regions of instability. I mean, you have these diffusive regions, and then you look at the boundary of these regions, and usually you have some of these essential continua, which separates the annulus into two parts. So you had the dynamics here. You have this region of instability here, and you're going to find, oh, there is some boundary of the annulus here. Each one of these is sort of an essential continua separating the annulus in two parts. And we already treated what's happening inside the regions of instability. We need to discuss a little bit what happens in essential continua. Thing is, essential continua can support more than a single rotation number. If you look at an essential continua in the annulus, just any dynamics on the annulus, the fact that you have an essential continua which does not have interior does not guarantee that every object in that continua is going to have the same rotation set. There is several different examples. For instance, the Virchow attractor. Anyone has ever seen this? And it's an attractor that has a rotation interval. It doesn't have a rotation set. Or you can have this sort of Walker example where the dynamics in here is just an irrational rotation in the boundary of this thing. This is a cantor, you're just rotating like a cantor set, but they wrap around this circle in such a way that when you look at the dynamics in this circle, then every point is fixed. So this is a dynamic in the annulus, and the annulus here, this point and infinity make an annulus. And okay, I look here and I say, okay, this invariant continua, I can see points which have a rational rotation number, I have points which have zero rotation number. They are in the same continua and they coexist. It's not because I don't have interior that as this object cannot have more than one rotation number. But in the error-preserving case, there's this important work by Andrés Koropecki, Patrice Lecalves, and Misan Nassili that say that if you have an essential continua whose interior is inessential, so if you don't have anything which is thick, separating the annulus in two parts, any of this continua which separates from one boundary to the other, then it can only have, if the dynamics is error-preserving, you can only have one single rotation number in this object. This object cannot comport at the same time different rotation vectors. Any dynamic which has this behavior in this sort of continua needs to be dissipative in some sense. You're going to have something that is sent inside, some region which is sent inside itself. You cannot have, it's going to be a wandering dynamics. It has wandering domains. And for those who understand a little bit more, I mean, if I have here in the annulus some essential continua, and then this thing here, this region below the annulus is some sort of U minus is homeomorphic to open annulus, and there is something which is called the prime end rotation number of a homeo of the open annulus. And I don't want to get much into that, but you can define like a compactification of this region to a really nice annulus such that the boundary is a circle and the dynamics extend it's the same here, but extends continuously to the boundary of this. But it's just just from this pink region to this annulus is going to be defined. And you're going to have a good rotation number of this top boundary, which is the prime end rotation number. And the theorem says that, okay, if you have some invariant set here, which is in the boundary of the annulus, and the dynamics is error-preserving, then the rotation number in this invariant set is the same as the rotation number that you find for the compactification, for the good model. So in some sense, you can always go to this good and nice compactification, study what happens there, and whatever rotation number you see here in this part, it's going to be the same as the one you see in this region. Okay, so let me try to give a quick, try not to be too complicated thing, but just try to give an idea of how do we put everything together. So how to string together all the results we have so far. So the idea here is we already have this is my rotation interval, AB, and I'm going to take some rho 0 in my interval AB, and I'm going to try to see if I can find a compact invariant set that realizes rho 0. So the idea is, the goal of the theorem is to prove that for any rho 0, I can find a compact invariant set that realizes rho 0. Well, I don't know if rho 0 is realized or not, but at least at the beginning, but the idea is that I can approximate rho 0 by a sequence of rationals inside my rotation set. And for every rational, I can find a periodic point realizing this rational rotation number in the rotation set. So I have here A, B, rho 0, and I find here a sequence rho 1, rho 2, rho 3, which converges to rho 0. And if I look in my annulus, I'm going to find here some Z1, which is a periodic point of rotation number 1, rho 1. Z2 is a periodic point of rotation number rho 2. And they all converge to some point Z bar which is the limit of this rotation, these periodic points. And all of them have a rotation number of rho 1, rho 2, rho 3, all going up to rho A to converging to rho 0. Okay, and Z0 was the limit. And the idea is, okay, now I would like to show that the rotation number of rows of Z0 is rho 0, but this does not need to happen. It's really easy to construct examples when this is not true. You have a sequence of periodic points that converge to a point, and the rotation number of the limit is not the rotation limit of the rotation numbers. So we try to solve this in a different way and say, okay, if my Z0 was in the interior of some region of instability, then in this region of instability, I have rho 1, rho 2, rho 3, all the, at least for points sufficiently close, I have all those periodic points. And then I can apply the result that says, okay, in a region of instability, my rotation set is the same as the rotation set, as the closure of the rotation set of the Aubry-Maher is the same as the rotation set of the measures, which is an interval. So if I was here, if this Z0 was in a region of instability, I could already finish and say, okay, I'm done. This is good. I know that this happens. If Z0 is not in a region of instability, what happens is that if Z0 is not in a region of instability, I can find some compact set K, which is an invariant annular continua, essential continua, such that Z0 is here. I say, okay, I have these points converging to Z0. I have this K, and I would like to show that this K has the rotation number of the limit of the individual points which I put here. But this does not need to be true, at least, because it's not because I have this K, which is the invariant essential continua, that the rotation number of this guy needs to be the same as the rotation number of the points approaching it. It doesn't need to be the same. This would only work if my K was stable. Why? Because if K is stable, meaning that any point that starts close remain close, if it has some invariant region which is invariant, a sequence of invariant regions which contain K, since I know everyone here moves with the same speed, then sufficiently close, everybody needs to move with a speed which is comparable to the speed that we had before, so that the rotation number cannot be large. The only way that I have a point here which has a rotation number which is different from far from K is if it spends time here and then it goes down, then it rotates with some strange speed here and then it comes back. So if I have a stable invariant annular continua, I'm good. So the idea is, how can I construct this stable annular continua? And this is...
Oh, sorry. So therefore, your Aubry-Maher set is going to be this invariant continuous as separate.
I'm going to, if I have this invariant continua which is separated, and this continua is stable, then yes. Meaning okay, that, but the thing is, it might not be stable. So I'm going to find either a region of, I'm going to find a trichotomy just now, in just a second. I'm saying, okay, I have this annulus. How do I, the idea needs to be a little bit more refined. I say, okay, I have this point Z0, and I take a small disk around Z0 of radius epsilon, the B epsilon of Z0. And then I take here what is the full orbit of this disk that contains Z0. So I have the disk, it goes around, well, but the dynamics is non-wandering, so it needs to intersect again, and then it starts intersecting again, and then you look what happens here. And I say, okay, these actually form some region which needs to be, and well, if you close the holes, you're going to find an annulus. It cannot be a disk. It cannot be a disk because inside this disk, you have periodic points of different rotation number. And you cannot have an invariant disk with two different rotation numbers inside this disk in the annulus. So what you find is that, okay, I started with the Z0, and for every epsilon, I have here my annulus, and I find some small annulus U epsilon, then I take some other smaller epsilon, and I find some other invariant annulus U epsilon linea. And I can take, just, okay, this should be the intersection of the closures of all this U epsilon. And this C is going to be an invariant set. And with the property that any point in C can be, so if I start sufficiently close to Z0, I'm going to be able to go to any point in C. So it means that this set C in the annulus is some region. Here is my Z0. This C contains Z0. It's an annular thing because I'm taking the nested intersection of closed annulus. And this set is something, either is something like this. This is one case 1. Then there is the second possibility, which is that C, okay, this is C. The second possibility is that it's like this. This is Z0, and this is a region of instability. And the third possibility is that it is like this. It can actually be, and here is my Z0. But now I have 3 possibilities. The first possibility, and these 2 possibilities, I have regions of instability. And in the third possibility, which is this case, here, C is stable. Just meaning, okay, I took this nested secret of annuli, and in the end, I either had some region of instability with Z in the boundary, and then the boundary of the region of instability is going to realize my rotation number, or some region of instability with Z in the interior, and then I can use the general theorem. Z does not need to be the point that realizes the rotation rho 0, but I have some minimal set there because I have some sort of horseshoe inside that realizes everything I want. Or this set is stable, and since this set is stable, the rotation number here is going to be the limit of the rotation numbers of the other things. So the set C all rotate with the same rotation speed, which is the rotation speed of rho 0, and it sort of ends everything. And
yeah,
I think I'm done with the time, so thank you. I mean, I have 2 more slides, but I just want to say happy birthday, Lorenzo, and thank you for everything that you've done for us in the mathematics here. Thank you.
Thank you. Are there any questions?
I have a question. The last part. So the case 1 is basically you find the 0 is not included in any region of instability. Is that?
I mean, I'm not sure if it happens to be realized somewhere else, but in this case, it's not part of a region of instability. It's just some boundary. You can think of it, for instance, if you have the Dent-Twist case, then you don't have any regions of instability. There's just invariant continua.